Değerli katılımcılar, sevgili arkadaşlar, ülkemizin bilim dostu, bilgisever, güzel insanları. Hepinizi saygı ve sevgiyle selamlıyorum. Bugün yine TÜBİTAK Temel Bilimler Araştırma Enstitüsü'nün Matematiksel Fizik ve Uygulamalı Matematik Seminer serisi kapsamında bir araya gelmiş bulunmaktayız. Bugün son derece heyecan verici ve harika bir seminer gerçekleştireceğiz. Konumuz Hawking'in kara delik informasyon paradoksudur. Bilindiği üzere bilimde gerçek anlamda paradokslar yoktur. Bilimin ön cephelerinde her zaman paradokslar ortaya çıkmış, bunlar bir çelişkiye işaret etmiş ve bilim ilerledikçe bu paradokslar çözülmüştür. Kara delikler bilimi de bilimin ön cephesidir. Kara delik bilimi süper bilimdir. Ve bu nedenle bir paradoksun ortaya çıkması doğaldır. Fakat gerçek şu ki modern fizik, teorik fiziğin temellerini sarsmış gibi görünen bu paradoksun çözümü 50 yıldan fazla bir zamandır dünyanın en iyi beyinlerini meşgul etmektedir. Hawking'in kendisi de dahil olmak üzere birçok bilim insanı tarafından farklı dönemlerde farklı çözüm önerileri ortaya konulmuş, fakat tartışmalar yine de devam etmiştir. Son olarak bu yılın Mart ayında Hawking'in informasyon paradoksunun çözümüne ilişkin yeni ve oldukça ilginç bir buluş ortaya konuldu. Ayrıca bu buluş sansasyonel bir haber olarak uluslararası yazılı ve görsel basında ve bizim basınımızda geniş yer aldı. Söz konusu buluşu ortaya koyan grubun lideri İngiltere'nin Sussex Üniversitesi'nden Profesör Doktor Xavier Calmet bugün bizim konuşmacımızdır. Profesör Xavier Calmet, Hawking paradoksunun kısa tarihi başlıklı bir konuşma yapacaktır. Seminerimiz İngilizce olarak gerçekleştirilecektir. Dear participants, dear colleagues and friends, a very warm hello everyone and welcome. TÜBİTAK Research Institute for Fundamental Sciences organizes online seminar series for national and international audiences with the participation of distinguished scientists and great speakers of the world. It is my distinct pleasure and honor to inform you that this evening we have another wonderful episode of our mathematical physics and applied mathematics seminar series with very special speaker, a world-class expert in the field, Professor Xavier Calmet from the University of Sussex, United Kingdom. He has kindly accepted our invitation to join us for this seminar, and he will give a great talk under the title, A Brief History of Hawking's Paradox. Professor Xavier Calmet is faculty member of the Theoretical Particle Physics Group at the University of Sussex since 2009. After graduating from the University of Karlsruhe in 1999, he moved to the Ludwig Maximilian University of Munich, where he obtained his Ph.D. in 2002. He was then a postdoctoral scholar successively at the California Institute of Technology, the University of North Carolina at Chapel Hill, the Free University of Brussels, the University of Oregon, and the Catholic University of Louvain before settling down at the University of Sussex. His current research interests span the interplay between particle physics and gravitational physics, grand unification, quantum theory, quantum gravity, physics of small black holes, and the dark side of the universe, dark matter, dark energy, and information theory. With this, I want to invite Professor Xavier Calmet to the stage to begin his talk. Xavier?
Let me share the screen. So first of all, thank you very much, Alikram, for this very kind invitation and for this absolutely wonderful introduction. I would like to start by apologizing to the experts. I wasn't so sure at which level to give this talk. So I decided to be as non-technical as possible to make it accessible to younger students. But feel free to ask me any questions at any moment if I'm not getting to enough details for your taste. Interrupt me anytime, please. I may not see the questions if you raise your hand, so either Alikram will help by monitoring raised hands, or may just interrupt me, just unmute. So thanks again for having me tonight. Again, it's a great pleasure. And well, the aim of this talk is to tell you about some of the recent results we've obtained with collaborators from the University of Michigan, so Steve Hsu, Michigan State, I always get this one wrong, from the University of Bologna, Roberto Casadillo, and a PhD student of mine at Sussex, Volker Teupes, who just started his first postdoc as of a few days ago. So I will tell you towards the end of the talk about Hawking's paradox. I need to build up the story, basically. And obviously, Hawking's paradox is linked to black holes. So I'd like to tell you a little bit about black holes and the history. So what I do find fascinating personally is that the idea of black holes goes back long before general relativity and Einstein theory, namely to 1783 and Mitchell, who was a British gentleman, and Laplace in 1795, who independently started to think about the escape velocity that a body at the surface of a planet could have. And they have asked themselves what would happen if that escape velocity was equal to the speed of light. And very quickly, you can show that there's a limit, basically on the density of the object or its size. And they were looking at the wrong limit, actually. They were looking at large objects. But they came to the conclusion that you could have objects that were such that not even light could escape from their surface. And in the end of the day, that's one way that we think of black holes these days. So its history goes back to pre-Einstein's theory of gravity. So the more modern way to look at it goes back to Schwarzschild. So Schwarzschild solution, which was found in 1915. So basically, almost as soon as Einstein put his theory out. And that's a vacuum static solution, so very simple. And that's a very famous equation that you've seen everywhere that describes a space-time. And the important parameter here is what is called the Schwarzschild radius, which is given by 2 times Newton's constant times mass of the object. And basically, that implies, the way we think of it is that there's a singularity at r equals 0. There's the radius of the black hole, which is an event horizon. And you can even calculate in this theory what is called a photon sphere. And that's what has created so much excitement recently with the pictures of black holes you've seen in the press, including the one at the center of our galaxy a few weeks ago. So that's something that you can predict with Einstein's theory of gravity and Schwarzschild solution. So the way we think of black holes nowadays is really as or for most black holes, as the end state of a star. So it's a star that is fairly massive, that undergoes gravitational collapse. And a black hole is really the end of the end of the life of a star through its stellar evolution for if the star has the right mass. And that idea goes back to Oppenheimer, really. And also Oppenheimer was one of the first people to discuss models for the collapse of dust balls and see whether you could solve them. So then, sorry, don't know why, here. The term black hole really came up quite late, and it's due to Wheeler, who introduced this term, so more as a way to make fun of it. I don't think that he really believed in the existence of black hole. They were just weird solutions that he wasn't taking too seriously. And in the Soviet world, they were called frozen stars. So Wheeler was responsible for quite a few terms we'll see today that are connected to black holes. Now, one of the very important results in the field of black holes goes back to Penrose and Hawking. So that's the first time we'll be mentioning Hawking today, but we'll be mentioning his name many times in the next 40 minutes. And basically, they had proven some very nice mathematical theorems trying to understand when singularities would form. And obviously, singularities are bad because that implies that the physics as we know it has to break down. And so they came to the conclusion that naked singularities should not exist. So you would have to have an horizon around them, basically, to shield them from us so we cannot see them. And basically, you have such theorems both for black holes, but also for cosmology. And one of the things we've shown in the last few years is that the theorems may not hold or do not hold in quantum gravity. So in terms of when black holes form, again, Penrose was one of the key players, and I cannot resist to explain to you what a closed trap surface is. So imagine you're sitting at a point here, and you flash some light in all directions. At some later time, you can define an envelope S1 and S2. And if both S1 and S2 are smaller than S, then you can prove that you have formed a black hole. So that's enough to prove gravitational collapse. And that's a technique that has been used, for example, to demonstrate when black holes would form in a collision. Oh, there's a question. Oh, yeah, sorry. So that has been used to prove that when a black hole will form in the collision of two particles or two planets with a non-zero impact parameter. So again, this is beautiful work that has accumulated over the years to demonstrate when black holes would form. Now, going back again to Wheeler, again in the 60s, he coined the expression no hair to characterize black holes, because black holes are extremely simple objects. So you have a star, which is a complicated construction, if you want. It collapses to a black hole, and is almost, what remains is extremely simple, to the point that you can characterize the remaining object, so the black hole, by its mass, its spin, and potentially its charge, if it has a charge. And this simplicity led Wheeler to coin the term no-hair theorems, basically to describe the fact that black holes are a very simple object in a very cheeky way, because you can think of the skull of a bald person who may look very simple with little feature. So again, Wheeler's contribution to black hole physics was essentially in finding names to make fun of it to some extent. I'm exaggerating, obviously, a little bit. So black holes are interesting for theoreticians like myself, because they are an indication that something goes wrong with physics as we know it. And the real issue with Schwarzschild black hole is not the singularity at the horizon, because that's not a real singularity. It's a coordinate singularity. So you can find smart coordinates that allow you to follow the path from outside to inside. It's really at the R=0 point, if you want. And to see that, you can calculate the invariant that consists in contracting the Riemann tensor of itself. And you see that that invariant, which should be an observable in a sense, will blow up at R=0. So that tells us that GR will break down at very short distances. So in that sense, we know to go beyond general relativity to understand black holes. And the first attempt to do that, to go beyond classical GR, was to start to implement some quantum effects. And things get very interesting for black holes when you start to implement when you start to implement quantum effects. So That was one of the first crucial contributions to the field by Hawking, who discovered basically that if you allow for the creation of pair and of particles close to the horizon of a black hole, one would escape, the other one would go into the black hole. And that would lead to basically a temperature. Bekenstein played important roles there as well, and temperature and entropy, basically. Now, that is the first known quantum effect, basically, for black holes. And that goes back to Hawking. And that's going to be the reason for the paradox that we'll be discussing in a little bit. So what's interesting is that the heavier the black hole is, so astrophysical black hole, the cooler they are. That also means the more classical they are. So obviously, if you want to look for quantum effects, you have to look for tinier black holes. And that's why a lot of these games are basically played on paper, because you don't have astrophysical objects that for which, as far as we know, quantum effects would be important. So all of this is done with pen and paper, imagining what happens to tiny black holes, quantum black holes, basically. So I've already told you a little bit why black holes are so interesting. So let me try to summarize things for you a little bit on that slide. So they're very simple objects, apparently, because you can completely determine them and provide all their properties by giving them masses, their charges, their spin. So they have no hair again. Now, what falls into a black hole remains into a black hole. There's no way to go out. Now, again, Hawking has shown that when you start to put quantum mechanics in the game, black holes are not really black, but they radiate, and that radiation we call Hawking radiation, and has a temperature. So basically, it has a thermal spectrum, and you may know that if you have a thermal radiation, that means that there's no information that is encoded in the radiation. And we will see that this is part of the problem, because the black hole will not remain static. It will radiate radiation. By doing so, it will shrink, and at some point, it would have evaporated. And the question is, what has happened to information? So that is a very simple way to think about Hawking's paradox. I will refine this definition of the paradox to be able to attack it. So black holes are really an ideal system to try to understand how to merge quantum mechanics, which is so important for particle physics. It's at the foundations of the standard model, and gravity. And now what is really wonderful is that, since the black holes have been around for a long time, as I mentioned to you now, 200 years and more, but we actually know that they do exist. So you can classify black holes according to their masses. Well, the first one, the Planckian black holes, so we don't know if these exist. So they're toys that theorists are thinking about. They're fascinating object because those are objects that would be of the Planck mass, 10 to minus 5 gram. And if they were out there, we could actually probe quantum effects with these black holes. Then you have primordial black holes. They could be of any size. So these are black holes that would be formed in the very early universe. They can still be around with us if they're heavier than 10 to the 14 gram. Now, what is really important about them is that they could be a component of dark matter, and I have colleagues at Sussex who are spending their time working on that, and they're viable candidates, and it's very interesting. Now, we don't know if these exist, but we do know that stellar mass black holes exist. So they must be at least 3 times the mass of the sun. And we see them also nowadays with collisions and gravitational waves. So we know that this is out there. Now, the intermediate black holes, I believe that astronomers have a strong suspicion that they're out there. I'm not sure we have examples of them, but that's not my specialty, so I would remain very careful with that statement. But they would be in a mass of range of 100 to 10 to the 6 solar masses. And then you have the supermassive black holes, which we know are there. They're typically at the center of galaxies. And again, recently people have provided these very beautiful and exciting pictures of the black hole shadows at the center of our galaxy. So black holes are real. And so we have to worry about the question of Hawking. So one of the reasons we were able to make progress is that in the last 5 to 10 years in my group at Sussex, we made a lot of progress in understanding how to make calculations in quantum gravity. And I won't have much time to go into great details, but I'll give you an overview of the motivation and techniques for this work. So obviously, we want to try to describe general relativity quantum mechanically, and that's a real challenge. You know that if you linearize general relativity and start to quantize the theory in a naive way, you end up with infinities, so the theory is not renormalizable. And that's one of the reasons why people have given up the naive quantization of GR and look for more complicated constructions like string theory, loop quantum gravity, you name it. But again, I'm a simple person and I would like to try to understand as much as we can about quantum gravity using quantum field theory techniques. Now, maybe in a very provocative way, I will argue that if we have methods that enable us to do calculations up to the Planck mass, we may not care so much about going beyond that because we'll never probe physics beyond the Planck mass. And first of all, this is a fantastic energy, and all experiments on Earth are done at energies way below that. If you look at cosmology, we know that inflation took place below the Planck scale. And the other thing is that if you were to try to pump, if you had access to these fantastic energies, so the Planck scale and beyond, if you had a collider that would enable you to go to these scales, to these energies, when you try to probe distances shorter than the Planck scale, you would form small black holes. And basically the idea is that you pump so much energy into a small region of space-time that it would collapse into a black hole and you would not be able to see anything. So one way to think about it is that we don't have pointers that are fine enough to probe distances shorter than the Planck scale. So from that point of view, effective field theories, which is what we'll be using, might just be all we need to discuss physics up to the Planck scale. And as physics is an empirical science, that might be all we need. So the goal is really to make the link with observables. Again, we're physicists, we're trying to make connection with experiments. So obviously the effects we're calculating are most of the time extremely tiny. So sometimes you're trying to use these calculations to compare them with thought experiments. But what I like about this approach is that it's very conservative. So you're using techniques that you understand very well. They're compatible with what the other forces of nature we know. So we're using basically quantum field theory that is so important for the standard model, and we're using GR, which we know seems to be the correct theory for gravity at low energies. So that program really is not new. It started in the 60s with Feynman, who had this attitude I like, which is shut up and calculate. So he would take GR, linearize it, and start to calculate amplitudes and try to see what could go wrong. So that was refined by Weinberg in the 70s, who really introduced the modern Wilsonian language of effective field theory to discuss GR, also quantum gravitational effects in GR. There was some beautiful work in the 80s by Barvinsky and Kovinsky, his PhD advisor, basically understanding all the subtleties of or most of the subtleties of the effective action. You know that when you calculate the effective action, you will end up with Wilson coefficients that can be gauge dependent. And you have, if you want to make predictions, that's an issue. So the work of Barvinsky and Kovinsky was really to propose what is called the unique effective action that enables you to have Wilson coefficients that are gauge independent. And that was a big issue in this business. And then Donoghue really had the courage to do calculations using these ideas in the 90s. And it really made it popular, I would say, among people interested in making calculations. And we took over these works and these, by these luminaries really and push them forward. And I think at this stage, we are now in a position where we can do calculations in GR. at the quantum level. And again, as long as we stay below the Planck scale. So one hope is that by working along these lines, we'll find some consistency condition that could tell us how to quantize GR, so how to go beyond the effective field theory techniques. What you need to assume is absolutely minimalistic. So you assume that GR is the correct low energy theory. So that tells you that quantum gravity has 2 degrees of freedom. You have the graviton that is massless. It has 2 helicity states, 2 polarizations. So those are your degrees of freedom. You need to tell me where you want to apply your quantum theory of gravity. So it could be the standard model, it could be unified theory, it could be inflation. So that tells you what T mean you should be. But with that information, I have everything I need to write down the effective action for quantum gravity. So you start from the Hilbert-Einstein action, you linearize your theory, and you start to calculate operators that are generated 1 loop, 2 loops, 3 loops, and so on. And you can essentially write down an effective action that is an expansion in curvature. So those are the leading order terms. So that's Einstein's theory. And you generate R squared, R mu, the same, the Riemann tensor. And then if you integrate out the massless graviton, again, that you're going to get these terms, but because the graviton is massless, you're going to get this log box over mu squared. So mu is a renormalization scale. Now, these are local operators. These are non-local operators. But that's the effective action at leading order, this curvature expansion. We can calculate it to any order. It's just becoming more and more tedious. Now, you would tell me, well, what have you reached? Because the theory is not renormalizable. So C1, C2, and C3 are used to absorb the infinities that you have in your diagrams. So we don't have a prediction for C1, C2, C3. On the other hand, the Wilson coefficients of the non-local part of the action are predictable. And they're model-independent predictions. They simply depend on the amount of degrees of freedom that you have integrated out. So that's a prediction of quantum gravity. And if you have an observable that only depends on the non-local part of the action, and in many cases we found, you get a prediction that is model independent. It doesn't matter whether the UV complete theory, string theory, or what it is, you have a prediction. Now, sometimes your observables will depend both on the local and non-local part of the action. Then you have to talk to a string theory friend to ask them what is the correct value for C1, C2, C3, for example, in their model. And if you look at papers by Dieter Lust, you will find that people are able to calculate these local part in string theory, for example. But again, we want to remain agnostic about the UV complete theory. So that's what we're dealing with. So the price to pay in our case is that we do not know the Wilson coefficient of the local operators. They're just 3 parameters in that sense. Now, I don't want to get into too much mathematics, but just to tell you what this log box is about, it's a distribution. And that's the only bit which is a little bit tricky when you do calculations. You have to get the right distribution, the right Green's function, basically. And that's in a 3+1 dimension, sorry, that's what you're getting in Cartesian coordinates. And so that's just to show you an example. I don't want to get into the details, but you can basically deal with these objects. Now, when you work at second order in curvature with in your action, it's enough to take L in flat space-time. If you go to higher order in the expansion, you need to take L in the curvature expansion as well. And again, you can do that. It just gets more tedious. It's just a matter of what you need to calculate. So let me show you the first the application of these effective action. Again, how we started to think about Hawking paradox. That was with this calculation, really. So if you take this effective action that I've just shown you and vary it with respect to the metric, you will generate corrections. So you have Einstein's equation here. You have your T mu nu, as I mentioned to you already. You have to tell me what you want to take for that. And you get these corrections at leading order or the quantum gravitational corrections, basically. And you have the local part and the non-local part. Now, the reason why I've shown you what logbox looked like is that this is what you need to calculate. So when you have decided what kind of theory you're going to look at, you can, so you tell me what your TMU is, I can express the Riemann tensor, the Ricci scalar and tensor in terms for this theory, and I can basically work out in perturbation theory what the effective action should look like. And all I have to do is to fold this distribution with the classical value for R for the Riemann tensor here. And then I do perturbation theory around the classical solution, and I get my quantum correction. So that's a generic, technique you can apply to any setting. So if you want to do quantum gravity in cosmology, you can do that with FRW. It could be your inflation metric, could be whatever you want. There are well-established techniques now to do these calculations. So we were interested in looking at corrections for a star. Again, before talking about black holes, a star is a little bit easier to think about. And the simplest model really you can have for a star is a dust ball. So you take your T mu nu that doesn't have pressure, you have a density that is constant, and you basically have a threshold where you have density rho 0 and empty space. So you know your solutions in GR for this model. I haven't printed them for you, but you can calculate. So it's basically the interior Schwarzschild for inside, the exterior Schwarzschild for outside. And we can use the technique I was describing to you to get the quantum correction to this classical solution. So we focus on the exterior regions. We have the TT and RR component of the metric. Now, what is really interesting and important here, if you look at this log part here, this term and that term combine to give you two contributions. The one that goes as r to the minus 3, and the other one that goes as r to the minus 5. And if you look carefully at the r to the minus 5 part, you will see that the coefficient of that term is proportional to Newton's constant squared, the mass of the star, times the radius of the star to the minus 3. So it is a quantum gravitational correction that is proportional to the density of the object. If you have a different star with a different density, you will have a different correction. So two source objects, the same mass, but different densities, give rise to different metric perturbations. So I will show you exactly what happens in a specific example. Now that's really important because in GR, again, you cannot differentiate the two stars. Birkhoff theorem tells you that the gravitational potential far away is the same. So now let me convince you that we can actually do, of what I'm telling you now. So we take, we're going to compare this one star to two nested dust balls with two different densities, so rho 0.1, rho 0.2, and we have different radii, so we basically split the star in two. The total mass is the same because we want the mass of the star to be the same, and the outer radius we're going to keep the same as well. And the quantum gravitational correction will be different for these two distributions. So we have a memory effect of what's in the star, basically, that we can see from outside. So again, in classical GR, the metric cannot distinguish between the two stars, but at the quantum gravitational level, we see a difference. And to be very explicit, here's what we're getting. So for the one layer star, we obtain a correction so that's the r to the minus 5 part, that goes this way with rs squared. And for the two layer star, we have this different correction. So clearly, the quantum corrections are different for the two stars. So that's where we got our intuition for black holes. So there is a quantum memory effect. Sorry, there's a bar that keeps on popping up in my screen. Let me try to get it out of the way. So sorry about that. So there is this quantum memory, and you can call it a hairy star, basically, because it's a feature that enables you to check or to know what went to the star if you want. Now, what I've shown you was for a time-independent static star. We can actually do the same calculation in a model that Oppenheimer proposed a long time ago. That's work we haven't published yet, which is in the writing, basically. And we can show that in this collapse model, when we work to the same order in perturbation theory, you can just replace the Rs by Rs of t in the equation I was showing you. And basically, we can check that the hair remains throughout the collapse of the star. So at some point, you will reach the Schwarzschild radius of 2gm, and you would have formed a closed trap surface. So basically, we have strong indications that the black hole keeps this hair, and that's basically quantum gravity produces a new kind of hair on black holes. So that was really our motivation to go back and study Hawking's question. Now, let me rephrase what I've shown you in a very explicit example in a generic way. So think of a compact source, and this source is going to be an energy eigenstate, and we will have a value, eigenvalue, let's call it E. We can write down a graviton quantum state psi g of E. And well, the obvious way to do it is exactly you would do for the U1 vector field for a Coulomb potential that is created by a charge Q. So you know that in QED, you can write the U1 field as an exponential of Q integral d3k. Then you have the Q of k, the linear combination of creation operators. So that's for non-propagating modes of the photons, so the temporal and longitudinal, that depending on the gauge, and you act on the vacuum where Q equals 0. Now, all you have to do for gravity is to replace Q by the energy eigenvalue of the source, and the coherent states then become the modes of, well, the temporal and longitudinal graviton modes. So in both cases, so both for gravity and for the gauge theory, for the U1, the asymptotic state is determined by Gauss' law via constraint quantization. So you could also think of it in terms of the amplitude techniques that are so popular this way. You know that you can recast amplitude calculations in gravity by double copies in gauge theories. And there's a similar technique for black holes that is very interesting. So basically, you can define an energy eigenstate, or so you can define a quantum state for the graviton. So it depends on E, which is a distinct energy eigenstate of the compact source, and it has different graviton quantum states. So you can write your semi-classical matter configuration as a superposition of energy eigenstates. And this will be supported, or the support will be concentrated in some fairly narrow band of energy. So here we write psi n, they're the energy eigenstates with eigenvalues En. And basically, you get the gravity state, so the graviton state as psi g as the sum over Cn psi g E of n. Now, again, the analogy with QED is clear. So the long wavelength photon coupled to the total charge of the object. Now, actually, there's a difference because you can play with charges in QED. You can have positive and negative charges. So you may have degeneracies. In the case of gravity, it won't be the case. You don't have negative masses. And so the long wavelength of the graviton couples to the energy eigenvalue of the compact object. So basically, a semi-classical compact source, a black hole, a star, anything like this, produce external graviton states that are complex superposition that are given by this object psi g. And what I've shown you earlier using these EFT methods is just a concrete example of this general result. But that is the way to think of the quantum hair in a completely generic way. Right, so now we're ready to talk about the information paradox. So again, the origin of this paradox goes back to Hawking in '76. And basically, because of his radiation, he argued black holes will decompose, they decay, and eventually they would be gone. And if the radiation doesn't carry information, what would happen to information that went into a black hole? So basically, in a more formal way to put it, you would say that black hole cause pure states to evolve into mixed states. Now, the better or best rather formulation maybe of the paradox goes back to Mature in the late 2000, early 2010. And he's got some beautiful reviews that you should really have a look at. And the way Mature does it is to track entanglement entropy of Hawking radiation that is emitted on a nice slice. So basically, Mature is a very smart guy, and he really wants to make sure that he knows what he's talking about, so he doesn't have to deal with quantum gravity and effects like that. So he takes a nice slice, which is a space-like surface that intersects both the interior of the black hole and the emitted Hawking radiation. And by remaining on these nice slices, you don't have to worry about strong gravitational physics in a sense, or quantum effects rather. So let me explain a little bit about Mature's formulation of the paradox. So Mature calls the modes that are outside of the horizon B. So there will be B1, B2, B3, and so on. And those inside the horizon, E1, E2, E3, and so on. So those are the pairs that are created by, those are the Hawking radiation. They come in pair. There's a B1, E1, B1 goes out, E1 goes in. And basically, he's got this slice, his initial slice in his foliation he's making. And that slice will only contain the matter state, so your black hole, psi m, and none of the radiation. That's before the first emission. And then you have the first step of the evolution of the black hole. So you emit two particles, E1, B1, and basically that state will be represented this way, 1 over square root of 2, 0 E1, 0 B1, plus 1 E1, 1 B1. So 0 and 1 are the occupation number of the mode. So that's your first emission. So the entanglement entropy here is straightforward. It's log 2. You see that directly here. So the next step, you're going to emit the second pair, B1, B1 we have already emitted, B2 and E2. And that state will look exactly the same when you replace E2 by 1 by 2. And basically, you do that pair by pair. So that in the end of the day, you end up after n steps, with a state psi, which is psi m, which is your black hole, whatever remains of your black hole, and a direct product with the first emitted particle, second emitted particle pair, and so on. So you have a tensor product with all the momenta, with all the quanta, and at some point, the pair, so since the pair creation happens far away, there's no connection to the matter state in the linear order Hawking process. So when you calculate the entropy for this object, it grows by log 2 at every emission. So if you have n emission, the entropy is n times log 2. So if you emit a large number of pairs, n is large, and your entropy grows and grows and grows. And that's the problem of Hawking radiation, basically, or the Hawking's paradox in Mature's formulation. At some point, the black hole has evaporated, so this part here is gone. The Bi, the quanta outside, they'll be entangled, but there's nothing for them to be entangled with because the E's have gone into the black hole and that thing is gone. And you have a system for huge amount of entropy. So that's the way to think about the paradox in a way that can be addressed within the framework that we have. So you basically show, in Mature's case, that you have a pure state psi m that has evolved into a mixed state, so these B's that are described by a density matrix. Now again, Mature is a smart guy. He knows that there will be quantum gravitational corrections to his argument. He calls them epsilon, but he argues that if you stay on one of these nice slides, the epsilons will not impact the result very much. The entropy would be reduced by a small amount, so you'd have log 2 minus epsilon, but this is not enough to account for the entropy. So this assumption, and this is what we are attacking basically, or this formulation rather, is limited by the assumption that you are on a semi-classical space-time background. What we will argue is that you have a very large number of backgrounds. Some of them would be classical because your black hole will keep on bouncing back and forth. So when it emits radiation, it's not going to be all the time symmetrical. So some going there, some going there. You may have some going in that direction, some going in that direction. So you would have the zigzag of the black hole, and those are macroscopic, path basically. So there's a classical space-time that will change. That is not taken into account here. And secondly, you have the quantum space-times. Every time you emit some radiation, the space-time changes, and you have to take this into account. So basically what we're saying is that black holes are a macroscopic superposition. And that's the way to look at it. And that's that if you do this, if you don't address the problem on one nice slice, but globally, then there's no paradox. So let me tell you now how we resolve the issue in more details. So we have seen that we've learned two things from our analysis of the quantum hair. So there's an asymptotic graviton state that of an energy eigenstate source that is determined to leading order by the energy eigenvalue, and you can express it explicitly as a coherent state that depends on this eigenvalue. Now again, assuming there's no accidental energy degeneracies, and that's not a strong assumption. You have folk theorems telling you that there are no degeneracies in gravity, and also you can, if there were some, they would be broken very quickly by quantum gravitational effects. So this is not a strong assumption. But assuming there's no accidental degeneracy in energy, there's a one-to-one map between the graviton states and matter source states. That was the quantum hair I was showing you. So that's the information we have about the inside. So semi-classical matter source produces an integral graviton state. Now, the other information is that in this specific model we looked at, so when you, the graviton loops, the fluctuation of the gravitational field, produce corrections to the long-range potential in the case I've shown you with this model of the star at R⁻⁵, and these coefficients depend on the internal state of the source. So it's an explicit example of how the graviton quantum state that corresponds to the semi-classical potential encodes information about the internal structure, the internal state of the black hole. Now, the beauty of all of this is that none of these arguments depend on the UV complete theory of gravity, of quantum gravity. It's all based on effective field theories and things we understand very well in quantum mechanics and things we understand very well. So let's look again at Hawking's paradox in our, or the evaporation rather of a black hole in our case. So we start by writing the quantum state of the exterior metric. So you can think of it as a quantum state of the, we could do the same for the, well, it's a quantum state of the exterior geometry. So psi I as a sum over n Cn psi g of En. And if you want to write it in terms of the geometry, you put a G here. So it's a semi-classical state. And again, it has support that is concentrated in some range of energies E. And it's the support is where the concentration is where the Cn are the largest, which is what you always have in quantum mechanics, right? So there's nothing weird here. This is just quantum mechanics, the way you teach to your students. So we're going to assume, for simplicity of notation, not of physics, that we're going to write only G of E here. And we're not going to write the other quantum numbers. It doesn't mean they're not there. We just, by G of E, we mean the metric in any other quantum number. So the energy in any other quantum number. So we're going to assume, again, that the black hole emits one quantum at a time. We want to understand what happens, what's different in our case from the case of mature. And in the end, the final state would have n radiation, and we write it like this, R1, R2, R3, up to Rn. Now, by the R, we mean the energy gap. So every time your black hole emits a radiation, its energy drops a little bit. So that's the amount of energy by which it drops, delta I. The momentum pi, the spin si, the charge qi. So that's what we mean by the R's. So the final radiation state can be specified by the values of R1, R2, and so on to Rn. We're going to have the amplitude for the emission of a quantum Ri from the exterior metric state psi g. So we're going to call it alpha E Ri. So to leading order, this is just the thermal result that Hawking obtained, but we can calculate quantum corrections to this with our within our framework. So that's the amplitude. And so even if you don't like this effective field theory approach, you can think of alpha. So there will be correction to Hawking's result for alpha coming from either perturbative corrections that I'm showing you that would go as entropy to the minus k, or non-perturbative effects, so that would go as exponential minus s. So the tiny effects, those are the epsilons that Mature we're discussing, but there will be some additional dependence on E and Ri that will emerge. So this is really, basically a consequence of the quantum hair. So these corrections that depend on the internal state of the black hole are there because of the quantum hair. Now you may tell me, but these are very tiny effects. These are the epsilons of Mature. Why would I care about it? And I would ask you then to please read some beautiful papers by Steve Hsu and Raju and his collaborators from 2012 and 2013, where they have shown that very tiny corrections of the type exponential minus s, so that's the worst case scenario for us. Those are the non-perturbative corrections, they're the tiniest. But these are enough to purify a maximally mixed Hawking state because the dimensionality of the Hilbert space is so large. So the epsilon do matter. You cannot ignore them. So here's now the picture we're proposing for the black hole evaporation or evolution. So your black hole emits the first radiation Ri, so R1, sorry. So you go from your state psi g, g, en that I've explained to you in the previous slide to a state Cn alpha En R1. Then you reduce the energy of the black hole a little bit by delta delta 1 R1, and you're summing over N and R. So these are all the quantum numbers. So here G reflects to, or is the exterior geometry, again, as I've explained. R1 is the radiation. And then you have step 2, you can emit your second radiation pair. So you have R2 here appearing. So the amplitude for R1 is still there. Then you have the amplitude to emit R2. So this energy is a little bit reduced. That's what appeared here. And yet you reduce again the energy of the black hole because you have more energy going away. And that's your new state. And at the end of the day, the geometry is gone, the black hole is gone, and you end up with a final radiation state that is a sum of all the radiation that have been emitted, but looks like this. So Cn alpha of En, R1, and so on and so on. Now, let me reproduce this equation for you, and we're going to discuss it a little bit. So here we drop the geometry because, again, the black hole has disappeared, doesn't exist anymore. There's no horizon, and space-time is essentially flat. And what we see here is that the final radiation state is a complex superposition which depends linearly on the initial states. And on the time reversal, the radiation state evolves back to the original black hole. So that's basically unitarity, and that's the resolution to the paradox. So there's no paradox. The information is encoded in Hawking's radiation because of the quantum state. Sorry, because of the quantum hair. Right, sorry, I'm running late. So let me come to the conclusion. So hopefully I've convinced you that we now have very well established effective field theory methods that enable you to do calculations in quantum gravity in a model-independent way. That depends on the observable, obviously, but in this case I've shown you, you've seen that there was no C's appearing in my metric, so it was only due to the non-local part of the action. We've seen that for a star, there's a quantum effect that is a memory effect, and that extends to black holes. So this memory effect is a quantum hair for black hole. It's a new kind of quantum hair, and we have information about the black hole, what went to the black hole, if you want, that is encoded outside in the gravitational field. And we have presented a generic expression for this quantum state, so the gravitational field. And I've used these results to show you how we escape Matour's argument and how we basically solve the paradox. And in this framework, it's obvious that the evolution of a black hole is a unitary process. Thanks a lot for your attention.